So as we planned, so let us now talk about Noetherian rings, and main topic is this. And of course, as an application of the concept, this concept will be structure theorem of finitely generated abelian groups. So we'll start with a proposition. The following conditions on an R module V are equivalent. First statement, that every subgroup is finitely generated. Every submodule, first I'll talk about modules, and we are going to use as, well, we are going to finally talk about Z modules, because objective is to understand abelian groups, finitely generated abelian groups. Okay, so this is my first statement, and second statement is ascending chain condition. In short, we write ACC. That means, what is it? There is no infinite, strictly increasing chain W1 containing W2 containing, so increasing, so let me write like this, of submodules of V. So there, these two are equivalent. What do we mean by this? We mean that if I have 1, then 2 is automatically true. So I assume 1. I'll try to understand how 2 is true. Suppose I have a chain. Suppose W1 is contained inside W2, and so on. Submodules of V. So we have to justify that if this is infinite, then this this cannot be strictly increasing. Okay. Let capital W be the union of these submodules. So it's not difficult to see that this is a, in fact, this union is a submodule, because if I have 2 elements from here, then their difference, if I have 2 elements, say U and V are belonging to W, then I can say that they are belonging to some Wi. I mean, one can say that U is in Wi, V is in Wj. So if I is maximum of the 2, it is in both. It is, both of them are in Wi. So that their difference is in Wi. Okay. And similarly, any element I pick, its multiple will be in Wi. Okay. So combination, all combinations of U and V will be in Wi. So hence it is in W, right? So that W is a submodule of V. Okay, but one says it is finitely generated. By 1, W is generated by, say, V1, V2, V, say S. Okay, this is by assumption. Then V1, V2, Vs belongs to some Wk for some k, by definition of W, because one may say that small vi belonging to some Wi, or small vi belonging to, say, Wi Ji. So then I can pick maximum of the maximum of Ji's, and if it is k, then I can say that V1, V2, Vk are in Wk, because this chain is increasing. So is it fine, or do I need to explain more?
It's fine, sir.
It's fine. Okay. So all of them will be in 1 WK. So that what do I have therefore? Therefore, WK is equal to WK plus 1. Right? Next one, and so on. So I can have at most k many members in the chain. After this, all are equal. Okay, so we have 2. That chain is not infinite. So conversely, that means I need to show that I am assuming 2 and have to prove 1. This is what we mean by conversely. Let W be a submodule of V. I need to show that W is finitely generated. So I am given that there is no infinite increasing chain of submodules of V. So then I need to show that any submodule is finitely generated. So I pick a submodule of V, say W. So then I pick an element. Suppose small w1 is an element of V, element of W, the module I have picked, submodule I have picked, which is non-zero. If W is 0, then empty set spans. So maybe that remark I should say. If W is the 0 submodule, then empty set is a basis of, right, span generates W. This kind of thing we know. So therefore, I'm assuming that it is non-zero, and I pick an element from which is non-zero. So then I'll say that if W is different from the submodule generated by W1, then we can pick one vector which is in W but not in the span of W1, the submodule generated by W1. If they are equal, then I am done. That, right? Otherwise, the W is finally generated, namely generated by just W1. So this way, I'll say that if W is not equal to W1, W2 together cannot generate W, then we can pick a third element in W, which is not in the submodule generated by W1, then W2, and so on. So we get a increasing chain or ascending chain of submodules of V. So say W1, which is generated by small w1, W2 generated by W1 comma W2, and so on. So what is the assumption? Assumption is that there is no infinite strictly increasing chain, since by 2, by hypothesis, by 2 means by hypothesis, maybe I write by hypothesis. What will I have? W have to be equal to small w1, w2 generated by some wk for some k. Otherwise, I will get an infinite strictly increasing chain, because this relation, this containment is strict, proper containments. Okay. So if I have hypothesis, the given hypothesis, then this is not possible for infinite sequence. So at some stage, I have to say I'll get that W is generated by W1, W2, Wk for some k. Is it fine? So 2 implies 1. If there is a problem, I can explain more.
Oh, it's fine, sir.
Okay. All right. So this completes the proof of the equivalence of the 2 statements. So there is a definition. A commutative ring R with 1 is said to be a Noetherian ring if every ideal of the ring R is finitely generated. Maybe I write it in words. Finitely. So what we have, that ascending chain condition holds for the ideals of R. So therefore I can say, as a corollary of the proposition we just have seen, that a ring R is Noetherian. I mean, ring means a commutative ring with unity. Maybe I write in short. Okay. With 1 is Noetherian if and only if its ideals satisfy the ascending chain condition. That is, there is no strictly increasing ideals, infinite chain of ideals. Okay, so examples are obvious examples are principal ideal domains, right? Every ideal is okay, finitely generated here, generated by only one element, where F is a field, R Noetherian. So we'll see more examples, of course. We'll see more examples. Before this, another thing that corollary, similar to that obvious thing. Suppose R is a, okay, if R is a Noetherian ring, then every ideal of R is contained in a maximal ideal of R. Okay, so as a proof, maybe we can quickly see how the ascending chain condition is helpful. I am sure you can guess. You can maybe try to dictate. So students may try to dictate me how to go about it. Suppose I have an ideal. I is an ideal of R, and I want to know, I want to give an argument that I is contained in some maximal ideal. When I say maximal ideal, an ideal which is a proper ideal and which is not contained in any other proper ideal of R. Am I right? This is the definition of maximal ideal.
Yes, sir.
An ideal which is a proper ideal, and secondly, there is no proper ideal containing that ideal. So I have to show that such an ideal is there containing I. So what is the idea? Can you suggest, any one of you? Suppose I is not maximal. So why I should suppose this? Because if I is maximal, then I am done. It is contained in itself. If it is not maximal, then there exists an ideal of R such that I is contained inside I2. Why? How do I know this? Because I is not maximal, there has to be an ideal, proper ideal containing I, properly contained. Okay, maybe properly contained. So if, again, I'll say if I2 is not maximal, then there exists I3, an ideal of R, such that I2 is properly contained in I3, and which is a proper ideal of R. So thus we get a chain of ideals of R. What kind of chain? Ascending chain. I is equal to I1, containing properly I2, and so on. So, but R is Noetherian. Since R is Noetherian, this chain is not infinite. So what is the conclusion therefore? So there exists some k, a natural number, such that Ik is a properly contained ideal of R, and it contains properly some Ik minus 1, and that is, it stops, as chain stops at k stage, so that Ik is maximal. Beyond this, I cannot pick a proper ideal containing Ik. So that means Ik is maximal. So we don't need Zone's lemma kind of thing to find a maximal element here. So, okay. So another theorem related to Noetherian ring. Let R be a Noetherian ring. Then every submodule, R submodule, of a finitely generated R module is finitely generated. Proof. Suppose the given module, R module, I am giving a name, call it V. Okay. So suppose the module V is the free module Rm, so that it is generated by M elements. Okay. For M equal to 1, I do not have to prove anything, because for this, every submodule of R, because M equal to 1, so V is R. I mean, here this R means V equal to R, is an ideal of R, right? By definition of ideal, R submodules of R are nothing but the ideals. This is by definition. So every submodule of R is finitely generated. So next we'll assume that M is bigger than 1, and we use induction. Okay. Consider the projection Rm to Rm minus 1. Now induction hypothesis is that we assume the statement for V equal to Rm minus 1. Okay, we assume the statement for the free module, R free module, which is generated by M elements, whose basis has got, whose rank is M minus 1. So I need to prove it for rank M. So if we call this map as pi, I mean, I need to say which projection I am looking into. So this I am sending to first x1, x2, xm minus 1, and I just ignore the last component. Okay, so that whose kernel is, what is the kernel? x1, x2, xm, such that x1, x2, xm are minus 1, 0, right? By definition. So therefore, what can I say about this kernel? Is it a free module? Students can comment about the kernel. Anybody would like?
Yes,
Yes.
sir.
Yeah. What is the
EM is generated by EM.
EM? Correct. It is generated by EM. So this is isomorphic to R, right?
Yes.
That's not a problem, I think, right?
Yes, sir.
Okay. Then suppose W is a submodule of Rm. So what do I need to prove? That W is finitely generated. Maybe full stop here. Let phi defined from W to Rm minus 1 by what? I restrict pi to W. What do I mean by this? Phi of small w is pi of small w. Because domain group for pi is Rm, whereas domain group of phi is W. That is how they are different. Otherwise, where images are concerned, if I have an element from W, they match. Okay. So then what is your comment on the kernel of phi? Kernel of this map. Can I say that this is obtained by intersecting W with the kernel of pi? Am I right? Is it fine? And what is the kernel of pi?
R.
It is R. So therefore, can I say that? So this is a submodule of kernel pi, which is isomorphic to R. So therefore, what can I say by case 1? That kernel of phi is finitely generated. Is it okay?
Yes, sir.
Kernel phi is finitely generated. Say kernel phi is generated by V1, V2, VR. Okay, this is one thing. Next, what about the image? Phi capital W, I mean the range of phi. Range of phi is a submodule of Rm minus 1, right? Can I say that by, since this, I have by induction hypothesis. What is the induction hypothesis? For rank less than M, the statement is true. What is the statement? That submodule of Ri, I less than equal to M minus 1 is finitely generated. That is, phi W is generated by, say, finitely many elements. Say phi W1, phi W2, like this, phi WT, say. where this W1, W2, WT are coming from W. Okay. So why I know what? Generators of kernel, finitely many of them. There are only finitely many we need. And also for the range, we need finitely many to generate. So now we claim is that W itself is generated is finitely generated, and in fact V1, V2 up to VR, then W1, W2 up to WT, they generate W. This is the claim. Okay. Suppose small w is coming from W. Then what can I say? Phi small w is a linear combination of phi of Wi, because phi W1, phi W2, phi WT generates phi of capital W. Okay. So this means phi of small w minus summation AIWI, I equal to 1 to t, is equal to 0. That means what I have here, namely W minus summation AIWI, I equal to 1 to t, is coming from the kernel of phi. So this means this I can generate as a linear using V1, V2, VR. So I write Bj, Vj, j equal to 1 to R by assumption. I mean, by induction hypothesis, we got these R many vectors from W, which generates the kernel. Okay. So this means W is summation Bj, Vj plus summation Aj or AI Wi, I equal to 1 to t, j equal to 1 to R. So thus capital W is finitely generated. Next, so what we have done for free modules, we have just understood how this is true. So when it is not free, so let us assume that suppose V is a finitely generated R module, and let V is be generated by V1, V2, Vn. Then what I have? Then we have a map from Rn to V. Right? This we have seen before. Today also, just before the class, I just talked about this. What we get, that if I have any x1, x2, xn, each xi coming from R, then summation xi vi, I equal to 1 to n, is an element of V, and in fact every element can be written like this. So this map is a surjective map, right? Is surjective. Generated means that now if W is a submodule of V, then phi inverse of W, what do I mean by this? It is those elements in Rn, say U in Rn, such that phi of U is small w or belonging to capital W. Right? So this is a submodule of Rn. And by the first part, namely for free module, we know that submodules of finitely generated free module is finitely generated. Phi inverse of W is generated by finitely many elements, say W1, W2, Ws, for some elements coming from Rn. Now phi of wi, they belong to capital W, and this W is in fact generated by these elements. So that W is finitely generated. Is it okay that why every element you can write like this? Is it fine? Please tell me.
Okay, sir.
Yeah, if you have an element in W, why it is combination like this? Is it fine? So if you have W in W, so how do I know that this is a combination of phi of Wi?
Oh, there is a pre-image for W.
Hmm.
That is linear combination of W1, W2 till WS.
Okay. So this is all right. This is all right. Okay.
Yes, sir.
Okay. If it is fine, then I'll just proof is complete here as such, because for other finitely generated modules also this is justified. So in this process we have proved certain results, which I am just going to record here. We have also proved the following statements. Which I'm going to call as lemma. Let phi from V to V prime be a homomorphism of R modules. Part A, if V is finitely generated and phi is surjective, then V prime is finitely generated. This is fine, right? I'll simply take a set of generators of V and then their images under phi. They will generate phi prime, right?
Phi inverse of phi prime.
Yeah.
Apply.
Yeah, I mean directly. Okay, directly you can write down any element in V prime is what? Phi of some element coming from V.
Any element from V prime is
Any element from V
equal to,
prime.
is
Yes.
equal to phi inverse of U.
Correct. Yes.
Of,
yes. So you write, and U is a linear combination, finitely generated. Some AI, some VI, I equal to 1. Right. This is what I need in the above one. So that what I know, this phi of VI together generate V prime. I didn't write all the steps. I'm just then you have to write phi U equal to summation AI phi UI, because phi is a homomorphism, and therefore U is a linear combination of phi of VI with coefficients coming from R. AI are coming from R. Okay, so maybe part B I'll write in the next page. Part B, if kernel of phi and range of phi are finitely generated, then V, the domains group, is finitely generated. Is it fine? We have proved this, right? In here.
yes, sir.
Which one is this?
For induction, we use the induction for n equal to m case, then car phi is finitely generated as phi
Yes.
w is finitely generated.
But
Now,
yes, that lemma we applied here. If you prove the lemma, and then you can come here to prove that W is finitely generated because kernel and image, namely phi W and kernel phi, are finitely generated. Same proof will be applied here, and we get the statement, right? Okay, then C, let W be a submodule of an R module V if both W and the quotient, say V bar, which is V upon W, the quotient, are finitely generated, then V is finitely generated. Okay. Moreover, if V is finitely generated, then V bar is finitely generated. Sorry. Generators of V I'll take, and then their images will generate V bar. So which I need here in this one. Okay. And C is obtained from A and B only. This is a different formulation of mainly statement B, right? Because for V bar is the range for the projection map, W is the kernel, right? Note that W is the kernel of some map, and V bar is the image of the same map. Sorry, V. For maybe I write eta here, not pi. Eta from V to V bar. Right. So then I have this special case. All right. So I'll go to next, more examples of Noetherian rings. And this is a well-known theorem called Hilbert basis theorem. It says, if we have a Noetherian ring, then a ring of polynomials over with coefficients coming from the given ring is again Noetherian. So if R is Noetherian, then so is Rx. And by induction, if R is Noetherian, then so is R x1, x2, xn. Okay. So main thing is proving the first step, that R is Noetherian, then Rx is Noetherian. Then by induction, we will get this statement that if I have finitely many variables or indeterminates x1, x2, xn, then the ring of polynomials with coefficients from R, polynomials in x1, x2, xn, any coefficients from R, is an Noetherian ring. So we have just to prove the first step, and it is the main thing. By induction part, I am not going to write. You can feel not difficult at all. All right. So first we write a lemma. This is very helpful in the proof. Let I be an ideal of the polynomial ring Rx. If A is the union of the zero element of R and leading coefficients of non-zero polynomials in I. Elements of I are polynomials. So leading coefficients of every polynomial of I of every polynomial of I are collected, and we are calling it A. Then A is an ideal of R. So given an ideal of Rx, we are writing an ideal of R. Namely, how do I get? I need to supply 0 to A and leading coefficients of polynomials belonging to I. Okay. So I will not write a formal proof, but students can suggest me what are the main steps here. So 0 element is already there. I don't have to worry about whether it is empty, non-empty, and 0 element is not there or not, right? So what you need to check that whether it is difference of any two elements is there, or whether multiplication by an element of R is again there or not. Okay. So will you please try, because that will be helpful in the proof. If you try to prove that A is an ideal of R, this will help me or help us in proving a Hilbert basis theorem. So 0 is already there in A, no problem with that by definition. Suppose A is an element in A. That means what? A, some A to the power m plus some coefficients. Some, say, summation bi xi, I equal to m minus 1 to 0, or maybe 0 to m minus 1. This belongs to I for some bi belonging to R. Okay. I have just written, when I say that leading coefficient of a polynomial is in A, so this is what I mean. There is an element in I, highest degree coefficient is called a leading coefficient. Same thing as the highest degree coefficient of a polynomial. Then somebody may wonder why to include 0 elements separately, because for zero polynomial, we do not define degree. So there is no highest degree coefficient for 0 polynomial. So therefore 0 element will never come, because highest degree coefficient is never 0. Highest degree coefficient is a non-zero quantity, right? So therefore, if I do not supply 0, I cannot be an ideal, because it will not have 0. So we have to supply separately. So now is it clear that if I have an element coming from R, then R times A is again in A. What is the reason? Because I can multiply by R to this, so that RA xm plus this is either highest degree coefficient or it will become 0. If RA is 0, then there is nothing to prove. So I'll say that RA is the leading coefficient unless RA is 0. If RA is 0, you don't have to prove anything, because it is there in A. What is the objective? The objective is to show that RA is in capital A. Is it okay? Are you able to follow?
Yes, sir.
Yes, sir.
Yeah. If RA is equal to 0, I have no problem. I am done already. If it is non-zero, then it is the leading coefficient of some polynomial, namely R times the polynomial whose leading coefficient is A. So therefore, RA is again in capital. Sorry, yeah, RA is again in capital. So this is how to see this. Similarly, suppose B is another element in A. So how do I know that A minus B is in A? Will you suggest me? So I'll have some polynomial B times x to the power some n plus summation ai x to the power I equal to 0 to n minus 1. Okay. So this is in I. So can you see that A minus B belongs to I? Sorry, A minus B belongs
n
to
greater
A.
than m,
Yes. Good.
then a to the x to the n, a into x to the n plus some polynomial belongs to I, and b into
Yes.
x to the power n plus.
Okay. So without, yes, you are right. Without loss of generality, I can assume this. One of them is bigger. So what I'll supply some coefficient, namely I'll multiply this thing by x to the power, sorry, n minus m minus b x to the power n plus dot dot. So then what will I have? I'll have a minus b x to the power n plus lower degree terms. Right? A minus b is the leading coefficient unless a minus b is 0. If a minus b is 0, then I have no problem. It is already in A. And if it is non-zero, then also I don't have a problem because it is the leading coefficient of a polynomial which is belonging to I. Right? This is in I, this is in I. Therefore, their combination is in I. So A minus B belongs to A. So this proves, actually, this is the complete proof of the statement. Although I said I will not prove, but we have discussed the complete proof, because the idea is that you understand what we are saying. Once we understand this, remaining part may not be very hard to understand. So we say proof now. Proof of Hilbert basis theorem. I have just abbreviated Hilbert basis theorem like this. Suppose I is an ideal of Rx. What is the objective? Hypothesis is that R is a Noetherian ring. I have to prove that every ideal of, I have to prove that Rx is Noetherian. So that means I have to prove that every ideal of Rx is finitely generated as an ideal of Rx. As an ideal of Rx. Okay. Let A be the ideal of R defined by the lemma above. So this is the first step. And suppose this A, I know that this is finitely generated. I'll say that alpha 1, alpha 2, alpha k generate this ideal as an ideal of R. That means every element in capital A is a linear combination of alpha 1, alpha 2, alpha k, where coefficients are supplied from R. Suppose fi belongs to I is the, okay, is such that this is an element of the given ideal of Rx, such that the leading coefficient of fi is alpha I, and this is range of I is 1 to k. I hope this is fine. So this ideal is finitely generated, and then we are giving name to these polynomials whose leading coefficients are these elements of A, these generators of A. Okay. By multiplying each fi by a suitable power or appropriate power of x, we can assume that degree of each fi is n. Is it okay? If see here, alpha 1 is the leading coefficient of f1. So I can say that alpha 1 is the leading coefficient of x into f1, and f1 belongs to I, therefore x into f1 is again in I, right? So therefore this degree assumption is fine. If you have a confusion, please ask.
Okay, sir.
This is fine. Okay, good. Still, any other person can ask a question. Don't have to worry that. Okay. Suppose P is the R submodule of Rx generated by, this 1 x xn minus 1. Okay. The same n, you see, I have some n here, and utilizing that n, the lower degree polynomials I'm trying to put inside P. All lower degree polynomials with degree less than equal to n minus 1. So the P consists of exactly those, and it is actually freely generated by 1x x to the power n minus 1. There is hardly anything to understand. Only thing is that we are assuming that we are giving a name to that free module of Rx. But this is a R submodule. Okay, I am looking in considering only the R submodule. Okay, so maybe I write that one. Note that B is a basis of P as an R module, and it consists of all the polynomials of degree how much? Less than or equal to n minus 1. Okay, this is what P consists of. Then W, we define it as P intersection I. So this is an R submodule of P, right? I is an R module and P is an R module. I'm intersecting them. I'm getting another R submodule of P, another R module, which is a submodule of P. Since P is finitely generated and R is Noetherian, this guy W is also finitely generated as an R module. Suppose this W is generated by H1, H2, HL as an R module. As an R module, then every polynomial in I of degree less than n is a linear combination of H1, H2, HL with coefficients from what? With coefficients from R. Because this is generated as an R module, so I need to supply from coefficients only from R. I don't need to go outside, because my whole ring is Rx, but now I am treating as an R module only. This is linear combination, LC. Okay, so Noetherian property we have used here. Submodule by finitely generated module is finitely generated, and R is Noetherian. Okay. Then claim is that I is generated by F1, F2, Fk. You remember F1, F2, Fk? These are the polynomials in I whose leading coefficients have been considered, and they generate the ideal capital A. And just now we have picked some ideals coming from W. Okay, so which is the intersection of I with, all polynomials of I whose degree is less than n. And so lesser degree polynomials are these H1, H2, HL. Okay. So claim is that this equality holds as an ideal of Rx. See, proof, I need to prove that this is I is generated finitely by certain elements of Rx. Okay, when I say finitely generated as R modules or ideals of R. Okay, so not much time is there. Hopefully I'll be able to justify. Some 4 or 5 minutes I need. I started a bit late. Let degree of, okay, I did not say what is this. Let consider the element G belonging to I. Maybe I write Gx, an arbitrary element from I. So I need to show that Gx is a linear combination of these elements F1, F2, Fk, H1, H2, HL with coefficients coming from Rx. Okay. Let degree of Gx be D. Case 1, that this degree is less than n. If it is less than n, it is natural to show that this is combination of H1, H2, HL only, because others are higher degree polynomials. Then G belongs to W, right? If it is of degree less than n, then by definition it is coming from W. All W consists of all elements of I whose degree is less than n. You see, this is how we defined. So this is generated by H1, H2, HL. Okay. Case 2, D is bigger than or equal to n. Suppose a notation is required. Suppose beta is the leading coefficient of Gx. Then Gx can be written as beta x to the power d plus lower degree terms. Then beta belongs to A by definition of capital A, because it is the leading coefficient of a polynomial belonging to I. Am I clear here? Is it fine? This beta has to belong to A by definition of capital A. Am I clear? Please let me know.
Yes, sir.
Okay. Now, since A is generated by alpha 1, alpha 2, alpha k, so I can assume what? Beta is some linear combination. Ri alpha I equal to 1 to k, for Ri coming from capital R. Is it okay? Since A is generated by alpha 1, alpha 2, alpha k over R. Coefficients I need to supply from R only. Okay. So now, also I remember that this alpha I is the highest degree coefficient of Fi. Okay. So using this, define Qx to be summation Ri, same Ri, x to the power d minus n, okay, times Fix. D is the degree of Qx now, because n is the degree of Fix, and I have multiplied by x to the power d minus n. So this term has got degree n, right? Now I am taking a linear combination of those with coefficients supplied from R, namely Ri for the I term. Okay, this is how I define Qx, and this guy belongs to the ideal generated by fx1, fkx, f1x, sorry, f1x, f2x, fkx, right? Because now as an ideal of Rx, you see, whole coefficient is actually coming from Rx, not only R. Okay, because I have to, I am multiplying by some power of x, namely d minus n may be positive. Okay. All right. So since degree is d and leading coefficient is beta, you observe this degree of Qx is d and its leading coefficient is beta. You see that? What is the leading coefficient of Qx? Can you see this? The leading coefficient is beta. What is beta? Ri alpha I. Alpha is I is coming from Fi, and Ri is here already. Is it clear that highest degree coefficient of Qx is beta? Please let me know. This is the main point. You see?
Yes, sir.
Yeah, Ri is a scalar, I mean coming from R, and highest degree coefficient of Fi is alpha I. So to know the highest degree coefficient of the term, I have to multiply them. So I'll get Ri alpha I, and then x to the power d minus n is to be multiplied to xix. So it's that whole term is a polynomial of a monomial of degree x to the power n, and then I'm taking some sum. So coefficient becomes summation Ri alpha I, which is beta. Right. So now the final step. Therefore, what I can say that Gx minus Qx equal to 0, or its degree is less than d. I mean, if it is 0, I cannot talk about degree. So I have to write either 0 or less than degree. By induction hypothesis, I mean, if it is 0, it is already in I. Induction hypothesis, what can I say? Gx minus Qx belongs to the ideal generated by F1, F2, Fk, H1, H2, HL. Sorry. So this is what I wanted to prove. So this proof is by induction on degree. Okay. So for lesser degree, we're done. We are assuming. Okay. When d is less than n, it is obvious. For d bigger than equal to n, we are proving by induction. Okay. So you convert, make the degree less than n, then it is obvious. Okay. So conclude that Gx belongs to, so Gx equal to Qx plus Gx minus Qx, right? This belongs to F1 ideal generated by F1, F2, Fk, H1, H2, HL. Okay. See, Qx by definition, it is in I. It is generated by this. And the difference has degree less. So therefore, it is coming from belonging to the ideal generated by F1, F2, F. And H1, H2, HL. Okay. F1, F2, Fk, and H1, H2, HL, comma. So therefore, their sum is there. So this completes the proof. Okay. So if you have a doubt, you can ask. And time is over. I shoot by 4 minutes. So I close here. So we'll continue with a structure of Abelian groups next class.